The impulse function delta of t is perhaps the most unusual signal you will encounter. To define it, we start with a gentler version. Consider u sub delta of t, a ramp that rises from 0 to 1 over an interval of width delta. Its derivative, delta sub delta of t, is a rectangular pulse of height 1 over delta and width delta. The crucial property is that its area equals 1 regardless of how small delta is. Now take the limit as delta approaches 0. The pulse gets narrower and taller, but its area remains exactly 1. In the limit, we get the unit impulse delta of t, 0 everywhere except at t equals 0, where it is infinite, yet its total area is still 1. We draw it as an upward arrow at the origin with a label of 1. The discrete time counterpart is much simpler. The Kronecker delta, delta of n, equals 1 when n is 0, and 0 for all other integers. Unlike the continuous time impulse, it has a finite value. Its stem plot is a single dot at height 1 above n equals 0, with all other values at 0. Despite its simplicity, it plays the same fundamental role in discrete time signal processing that delta of t plays in continuous time. Comparing the two impulse functions side by side. The CT impulse delta of t is represented by an arrow at the origin with unit area, while the dt impulse delta of n is a simple stem at n equals 0 with value 1. The CT version is a mathematical idealization that cannot be physically realized, while the dt version is a perfectly ordinary signal with finite amplitude. Both share the crucial sifting property that we will explore next. The sifting property is the most important property of the impulse function. It states that the integral from negative infinity to infinity of delta of t minus t0 times f of t dt equals f of t0. In words, multiplying any function by a shifted impulse and integrating extracts the function's value at the impulse location. Let us work through an example. Find the integral of delta of t minus 1 times the quantity 2t squared plus 1 dt. By the sifting property, we evaluate f of t at t equals 1. f of 1 equals 2 times 1 squared plus 1, which equals 3. The entire integral equals 3. A closely related property is the multiplication rule. When we multiply delta of t minus t0 by a function f of t, the result is f of t0 times delta of t minus t0. The impulse freezes the function at its location. For example, delta of t minus 1 times 2t cubed minus 1. Since the impulse is at t equals 1, we evaluate f of 1 equals 2 times 1 cubed minus 1, which equals 1. So the product simplifies to delta of t minus 1. Here is a tricky example. Delta of t minus 1 times u of t minus 2. The impulse is at t equals 1, so u of 1 minus 2 equals u of negative 1, which is 0. The entire product is 0. The scaling property states that delta of a t equals 1 over the absolute value of a times delta of t. Time scaling an impulse only changes its strength, not its location. Delta of 2t equals 1/2 times delta of t. Delta of negative 2t also equals 1/2 delta of t because we take the absolute value. For a shifted version, delta of 2t minus 1 equals 1/2 times delta of t minus 1/2. The impulse moves to t equals 1/2 with strength 1/2. Similarly, delta of 3t minus 3 equals 1/3 times delta of t minus 1. Let us summarize. Delta of t is defined as the limit of narrowing pulses with unit area. Delta of n is simply 1 at n equals 0. The sifting property extracts function values. The integral of delta times f equals f at the impulse location. The multiplication property freezes functions at the impulse point. And the scaling property adjusts impulse strength. Delta of at equals 1 over absolute a times delta of t. Next, we will connect all three elementary signals through derivatives and integrals.